All right, so back over here. All right, so you guys saw those video demos. We're thinking about scenarios that could possibly uh, be applicable to this conservation momentum. Okay, let me give you guys just a few notes here, and then we'll go solving these problems. Okay? So just to make sure everybody's on board with what we're talking about. You guys know that momentum is mass times velocity. Okay. Now, the physics way of writing this, the symbol for momentum is lowercase p. I'm going to throw a vector arrow over that. I've just been in the habit of doing that the last couple of years, so I'll just keep doing that. Mass is a scalar, so it gets no vector arrow, and velocity is a vector. Okay. So the direction matters. Okay. So we're talking about vector quantities. Well, except for mass, that's still a scalar. Okay. And we're going to apply this to collisions. Anytime you see a collision, think something to do with momentum physics, right? Or in the case of like Wanda throwing the baseball, which if you run the film in reverse also looks like a collision, right? It's good still apply, but we'll solve that one later. What's the unit for momentum? Right, so units. Right. Well, mass is in kilograms. Velocity is in meters per second. Okay, so that's it, kilogram meter per second. That doesn't have a special name like forces in newtons or energies in joules, which are composite units. So I'm just going to call this kilogram meter per second or unit of momentum. But I'll tell you what this is also equal to. It's also equal to 1 Newton second, which you more see when we're talking about like impulse, which is a change in momentum. So those units are the same though. Okay, and here's the big overriding principle that's going to let us solve a bunch of problems. Okay, conservation of momentum. Okay, momentum is conserved. This is true for the universe in general. This is true for closed systems. Closed systems, if there's no external force, I can say that the sum of momentum before the collision is equal to the sum of momentum in the system after the collision. This is pre-collision and post-collision. Okay, like that. All right, so yeah, lots of objects colliding. You can say what's the momentum before and after that collision, right? And the momentum has to be conserved. Okay. And there's reasons that you would not want to use other methods of physics, like conservation of energy is like a, well, here, I'll show you guys as we're going through solving these problems, right? It makes more sense, more to solve. Okay. All right, so you know what else I need to show you guys here is I've got some new posters hanging above, hanging on the ceiling, right? So here's how this is kind of going to look, right? We're gonna have objects that are headed toward each other. See, I'm keeping everything on just on one axis, like one dimension, like the x-axis, right? So this, we're just keeping this pretty straightforward. Although you could take all the things that you learned today and you could solve a bunch of crazy billiards examples. So if you have like bam, like glancing collisions, just take this into 2 dimensions. But we're just going to do 1 dimension. Got different masses, different initial velocities. Bam, they collide right there. Then what happens? Well, there's a bajillion different things that could happen. Okay? They might collide and stick. They might collide and bowling, bounce off each other. They might be like half the played tennis balls for like, they bounce off each other, but not very well. Okay? But regardless of which of those situations it is, this statement right here is always true. If you add up the mass times velocity bits before the collision and after the collision, they have to equate. Have to. Okay? Now, there are some special kinds of collisions you could have. This is one of them, perfectly inelastic, where they collide and bam, and then stick together. And you know, maybe they bam to the left, maybe they bam just stay still, maybe they bam move off to the right. But like I'm showing here, right? And this is a really similar setup. The only difference is the fact that they have the same final velocity. You could just factor that out. And also they act as like one giant mass post collision. Okay, so you guys got that. Okay. And actually, we're going to take this one. If you put it in reverse, you can solve the baseball question. Okay. So here's Wanda in the baseball, right, sitting at rest, and then she throws the baseball, and so it goes from right to left, sort of. Right. So it's like a collision in reverse. Okay. Okay. Now that's like one boundary condition. That's one extreme thing that can happen. It's called perfectly inelastic. But the other thing that can happen is this here is perfectly elastic. It's like the other boundary condition, the other extreme. What if two objects like bounce off each other as perfectly as they could ever bounce off each other? And the physics that distinguishes like a perfect balance is that not only is momentum conserved, which is universally true, right? This is always going to be true. Right? We're about to solve some of these, but also this very special condition happens, which is that kinetic energy specifically is conserved. So again, we're talking about whenever we talk about this elastic, we're talking about something like this, like Newton's cradle. Okay. And so not only is momentum conserved, but also if I add up the 1/2 mv squared before and after the each collision, that's also conserved. Okay. Now there is a result from all this. There's a solution to the system of equations, and it's right here. Okay. And I'm telling you guys this. If you didn't know this takes a lot of time to solve, a lot of paper. And this equation right here, not in a lot of physics textbooks, and also kind of hard to find on the internet. So I'll tell you guys what, if any of you are going to take physics in college, probably a number of you guys will. I think there's a good chance. Like I remember having to solve these type problems as a college student, and it took a lot of paper and a lot of time. Okay. But if you have this in front of you, you're like, all right, and just like jot this down. Like this is always the solution to the system of equations. Okay. So good to know there. All right, I've got for you guys, all right, how bouncy is something called coefficient restitution. We won't get to this today, but this is going to be one of your labs also. So we'll talk about this tomorrow, and also there'll be a lab, right? How bouncy is the ball, right? And I do have a more like professional looking poster, but it's basically this impulse, which is change in momentum, which is the area under force versus time. Also, we're gonna have to save that one for another day, but it's there hanging in a poster. Right, so let's get going here, start solving these problems. Okay. Now the first two are just conceptual type questions, so let's knock this out first real fast. Okay. See how many guys are following along so far. Two objects collide and bounce off each other so that the kinetic energy of the system is conserved. For example, Newton's cradle. What kind of collision is that called? Elastic. Yeah, that's like a perfectly elastic collision. Okay. Question number two. Two objects collide and stick together. Okay. And when that happens, some of the kinetic energy is converted into other types of energy. Might be energy of deformation. Maybe the temperature goes up a little bit, heat energy, thermal energy. Right. For example, two play ball stick together, one football player tackles another football player, and that's called what kind of a collision? Inelastic. That'd be like perfectly inelastic. Okay? Now a lot of collisions are somewhere between these two boundary conditions. So if you have two half-inflated tennis balls at football, it's neither exactly this nor exactly this, but it's somewhere in the middle. Okay. Question number three. Here's the first one we're actually going to solve. Two objects with these masses, kilogram, right, are going to collide head-on. Bam. Right. So what happens after the collision? Okay. Now, my numbers are different than your numbers, but we all have the same scenarios. So this page, here, I don't know if you guys want to like solve the ones in front of you or just write notes, but I guess it's up to you what you want to do. Okay. So number three. Okay. I'm going to get an axis where all the action is going to happen. Right. So this is like my x-axis where everything's traveling. I need a mass A and a mass B. Now mass A, I'm calling 1 kilogram, which is different on your paper. And mass B, I'm calling 2 kilograms, which is again is different on your paper. Okay, so I got this. Okay. I also need to give these guys some velocities. So let's go. Velocity A initial is like 3 meters per second. And velocity B initial, I get the same speed but opposite direction. So I'll call that -3 meters per second. Okay? And these two are gonna bam collide right there. And then what happens? We'll set up conservation of momentum and find out. So I definitely know collision physics. I'm gonna go to this. Sum of momentum initial equals sum of momentum final. And momentum initial, well, that's just mass times velocity for all the little bits. Added up. Added up is what the sigma is, right? So momentum is mass A, velocity A, then the sum of means if you're doing plus and doing mass B, velocity B. Oh, and those are initial. That's equal to, and I got mass A, velocity A final plus mass B, velocity B final. Just like that. Okay. Now let's just feed the numbers into the setup and make an equation and solve this thing. So I know the masses are 1 kilogram and 2 kilogram, right? So mass A, look at it, 1.0 kilogram. It's there, but also over here, 1.0 kilogram. Mass B, 2 kilograms, 2.0 kg. 2.0 kg. Velocity A initial, 3 meters per second in the positive direction. Velocity B initial, -3 meters per second, or 3 in the negative direction. Okay. So I got that. All going good so far. And looks like I'm some piece of information short. Okay. So what I've got so far just on this paper, like if I didn't know any other context, I would not be able to solve this problem. It would be ambiguous because, there's a lot of ways this collision can play out. Do these things boing bounce off each other? Do they collide and stick? Do they like have to play tennis balls? Right? It could be any of those. So I need some extra information, but I did give that to you guys. I told you guys one of the post-collision velocities. I said velocity A final. Now for my paper, it says -1 meter per second. So I'm going to pop that in right here, -1.0 meter per second. And now this is solvable, right? Again, any of those other situations could be solved with the setup. You just have to know one piece of information extra. So B final we're solving for. Okay. I see 3 units of momentum here. So this is 3 kilogram meter per second. I see -6 kilogram meter per second here. I see -1 kilogram meter per second here. And then plus 2 kilograms times VDF. Okay. So let's see, 3 plus -6, that's -3 units. Add 1 over to -2 units of momentum, divide by 2 kilograms. So cut through some algebra steps here. I'm getting VB final is equal to -1 meter per second. Okay. There you go. Okay. It's working out for you guys too. Okay. All right. Now, before I move on, I want to do a kinetic energy check, because if you think about it, like if you didn't know what was before and what was after, and you're just like looking at equations, or suppose you're just making up problems on the fly, you know, just like a bunch of masses, a bunch of velocities, say, I don't know what's going to happen. Okay. It might be hard to distinguish between what came before or after, or you might set up a problem that is, I mean, you guys can see like some kind of symmetry right here, right? It's like what was before, what was after. You just make up some crazy numbers, but you might end up creating something that's like physically impossible to happen, but you just wouldn't know. Okay? So the way you can check, the thing can give you some kind of arrow of time is a kinetic energy check. So I wonder, what is the kinetic energy before the collision, and what was the kinetic energy after the collision? So K naught and Kf. Okay? Because kinetic energy, if it was a perfectly elastic collision, it would be the same. But if it's anything other than that, if it's anything other than like a Newton's cradle situation, the kinetic energy must go down. Now, it's not because energy is disappearing from the universe, but it's because energy is diverted to maybe like deformation, heat, you know, like thermal energy, maybe sound energy, things like that. Things like non-mechanical forms that it's hard to quantify. So let's say, I'm just going to do this on my calculator screen. What's 1/2 times this mass times v squared plus 1/2, 1/2 mv squared is what kinetic energy is, right? Add it to this guy, 1/2 mv squared. And I'm looking at 13.5 joules of energy that it started with right before the collision. What about after the collision? So 1/2 mv squared plus 1/2 mv squared. Right? I'm dropping all the negative signs, but I can't for a couple of reasons. One is that if you square a velocity, it's just going to be positive anyway. But also, you guys remember energy is a scalar value, so it's just, you know, all right. So for both of you, you get 1.5 joules after the collision. Do you guys see a change? So there's like 12 joules of mechanical energy that's lost. Okay. and it doesn't disappear from the universe, just turns into like deformation and thermal energy, that sort of thing. Okay. All right. Now, it just so happens to be that my particular numbers work out to be one of those special kind of collisions. It's obviously not elastic because the kinetic energy changed, right? But do you guys see final velocity is the same for both objects? Whoa. So my objects happen to actually stick together. Right? Didn't have to work out that way, but I just coincidentally did. So there you go. Okay, guys good there? Next one, number 4. Now, number 4, I don't want to write out on paper because it's very similar to what we just did, right? Just set up equation. The only difference is I asked you guys to solve for a pre-collision velocity, but mathematically, it's not a whole lot different than what we just did. Okay, so you know a bunch of post-velocity information. But I want to talk about this one a little bit because what this could be really useful for is suppose that someday you are a forensic investigator and you show up to the scene of a car crash and you're trying to figure this out, like what happened here? So you see where the cars ended up. They definitely collided, so there's some collision physics. Oh, I remember I was back in Griffin's class, we were talking about like collisions. Okay? I see some tread marks, so I can figure out kind of where they collided and skid it off to get to that point, right? But then what happened before that? Like what happened like right leading into the collision? Like which car was traveling how fast? Like how fast were the cars going? Okay? That's exactly what you could use this for, right? Because you could know if I know the mass of each car and I figure out like after the collision, like how fast they were traveling, I could go figure out what was happening before the collision. Okay. So I'll just leave that one at that, but it's really similar to what we just did in number 3. Number 3, number 4, mathematically very similar. Okay. Number 5, 2 objects collide and stick together in a perfectly inelastic collision. Right, so given their masses and initial velocities, what's the final velocity of both objects? Okay. You guys see how here, like back up for a bit. You guys see how the last couple questions I gave you guys 5 numbers each? Like 2 masses, 3 velocities, two masses, 3 velocities. Okay. For this one, I'm only giving you 4 numbers, 2 masses and 2 velocities. So you would not be able to solve this unless you had the 5th piece of information. But the 5th piece of information is the fact that it is perfectly inelastic. Okay. Or you could just say they're gonna have the same final velocity anyway, so you can just factor that out. However you think about it. Okay, let's go solve this thing. All right. With that page. Okay. Number 5. Zoom out. See this. So let me get my axis going. Okay. Again, we're just keeping everything on one-dimensional axis. Just keep it pretty straightforward. So I've got a mass A and a mass B. This guy is 1 kilogram. This guy is 2 kilograms. Or your guys' numbers are probably different than mine, but something like that, right? Okay, mass A is traveling to the right at VA initial of 7 meters per second. And mass B is traveling the opposite way, pretty slow. So velocity B initial is -2 meters per second. Okay. These two are gonna bam collide together right about there. And then what? Well, since you know they stick together, that means you can solve this. Right? So perfectly inelastic. So I know collision, I'm going to do sum of momentum initial equals sum of momentum final. Okay. That's our framework for solving all these collisions. Okay. Combine that with the fact that you know this is perfectly inelastic. They're going to collide and stick. And I can say that mass A, velocity A initial plus mass B, velocity B initial equals, and then they're going to make one giant mass, MA plus MB times B final. Okay. And the question is, what is B final? Okay. Just like that. So, also, but before I get plugging and chugging, I think we can get a pretty good idea just by looking at the picture. You guys see 7 units of momentum to the right? That's what 1 times 7 is, right? Okay. And you guys see 2 times -2s, like -4 units of momentum this way. So 7 to the right and 4 to the left. Who's going to win, 7 or 4? 7. Yeah, it's a bigger number, right? So after these stick together, do you think they're going to continue to move off to the right? I think so. Should get a positive number here. Okay. Let's try this out. So I got 1 kilogram moving at 7 meters per second plus 2 kilograms, moving at -2 meters per second is equal to 1 plus 2 kilograms, moving how fast? Okay. That's not there. Okay. So I got 7 minus 4 is 3. So I got 3, and this is kilogram meter per second. And that's going to be 3 kilograms moving how fast? Okay. Oh, divide down 3 kilograms. Looks like I'm going to get 1 meter per second. Okay. So that's the solution to mine. Of course, you guys' numbers are different. For completion, let me run a kinetic energy check. Okay. And like I've been telling you guys, I guarantee there's going to be more kinetic energy to start than at the end. So what's K naught? What's K final? Okay. How many joules is this? So many joules. Okay. Let's run the numbers. Let's do this on a calculator screen. So it started out 1/2 times this M times this V squared plus 1/2 times this M times this V squared. There was 28.5 joules to start with. Right? Well, there must be less afterwards because this collision was inelastic. And so what's 1/2 times the combined mass of 3 kilograms times 1 meter per second being squared? Only 1.5 joules of kinetic energy after the fact. Yeah, so there was a lot of mechanical energy that was didn't disappear from the universe, but went into like deformation, heat, that sort of thing. You guys get there? Okay. Now, if you take this problem, let's say you film this whole thing happening, and then you run the film in reverse. That sure would look a lot like, maybe like throwing a baseball, right? Especially if you started from red, or like if this like came to rust or something, it would look pretty well exactly. So I know the next problem, number 6, involves like a grenade exploding, but before I do that one, I think this is a perfect time to solve that magic school bus problem. Okay? So sort of a lead into number 6. I guess it's a precursor to number 6. Okay. Let's go. Let's get Wanda up here. Give her a baseball cap.
Give her a grenade, actually.
I'm gonna give her a baseball. How about that?
I mean, number 6 says a grenade falling to the
Yeah. We'll get to the grenade. Right. So in time. All right. So this will be a step up to that. All right. So let's go mass of the ball. Okay. I do know baseball is like 0.145 kilograms, so I'll just go ahead and use that number. Okay. And you need the mass of Wanda. Okay. I'm just gonna make something up. I don't know if this is realistic, but it's just a number, so let's just go with it. Right. So many kilograms. And she's gonna chuck this ball, let's say relative to the field and yada yada. Right. We got the velocity of the ball is like let's go 20 meters per second. And also I need you to assign some kind of direction. So if left is negative and right is positive, I'll actually call this -20. Is that right? -20 meters per second. Okay. And then she's gonna head off. Velocity Wanda. Well, we don't know, but that's what we're trying to find out. That's the big question, right? How fast do you go back towards second base on this frictionless field? Okay. Okay, so I can still use conservation of momentum. Sum of momentum initial equals sum of momentum final. Okay. Again, if you filmed this thing and then you ran the film in reverse, it would look exactly like a collision. Okay. So how much momentum is there in the system when she's just standing there with the baseball? 0. Yeah. So there's 0 kilogram meter per second ever in the system. Okay. So when she throws the baseball, you've got 0.145 kilograms. So that's the mass going times velocity one way. Plus 60 kilogram mass times the Wanda going the other way. Okay. The momentum still has to zero out. Well, if some was negative, some was positive. Okay, so that could happen. That could zero out. Right? Add this term over here, divide by the mass. MV Wanda is, what is 0.145 kilograms times 20 meters per second, all divided by 60 kilograms. Kilograms cancels. And I'm getting 0.048 meters per second. I'm just reading my notes from earlier. The number's rounded a little bit, but that's pretty close. Okay. All right, so there you go. She will slowly head back towards second base. Yeah, the baseball is such little mass, compared to her. Baseball's going fast, she's going kind of slow. I'll check that. Right. And finally, let me do a kinetic energy check. Now, guys, how much kinetic energy was there to start with? 0. Yeah, 0 joules, because there was no energy motion. Everyone was just at rest. And after the throw, there definitely is kinetic energy. Whoa, where did all this energy come from? Let's think about that while I'm pulling this up. Down this from earlier. 1/2 mv squared plus 1/2 mv squared. It's something like this. Something like that many joules. Okay. Hang on, there was no energy to start with. Where did all the energy come from?
Chemical energy?
Yeah, like the chemical energy stored in our muscles, right? Right. That's where that came from. Which again, it's like a non-mechanical form. So it'd be really hard to count for with the stuff we've been doing the last couple of weeks, right? That's where it came from. Yeah. Right. And again, too, if you ran this film in reverse, it would look like a classic collision, in which case the kinetic energy would decrease, like going in reverse collision style, right? You guys get it? Right, so everything's checking out. It's all good. All good. Okay. Now let's do the actual number 6 with grenade. It's grenade time. Yeah, right. We're good. Right, so number 6. Got this grenade. It's flying through the air. Let's say at one point, I mean, it's probably like a parabolic type trajectory, but let's say at one point it's at the peak, so it's has this lateral type motion. Okay. I'm gonna give this guy a mass of 1 kilogram and an initial velocity of v naught of 15 meters per second. Okay. Now on my paper, that's where I'm getting the number. V naught is 15 meters per second. Okay, but it might be different on yours. Okay. Then this grenade at that moment is gonna bam explode into 2 parts. Again, to keep it pretty straightforward, let's say that the energy all goes into like lateral motion. So I've got this mass B of 0.6 kilograms and this mass A of 0.4 kilograms. And the mass A is going to take off. Okay, VA final of 20 meters per second. Notice that's faster than the original throwing speed. Okay, so what is VB final? Okay, now, VB final definitely has to be less than 15 meters per second. If this is kind of a small explosion, maybe it's just a little bit less than that. Right? If it's a huge explosion, suppose piece A took off like 10 times speed, like 200 meters per second, then piece B almost certainly has a negative velocity, right? It could go backwards, right? But it can't be greater than numerically like positive 50 meters per second, because that would violate conservation of momentum, which is how we're going to solve this thing. Sum of momentum initial equals sum of momentum final. So I got 1 kilogram at 15 meters per second. And it's gonna bam break into 2 parts. So there's this explosion right here. Bam. We got 0.6 kilograms moving at some velocity that we're solving for, plus 0.4 kilograms moving at 20 meters per second. Okay. So we got 15 units of momentum. There's 8 units of momentum. Okay, subtract that over and get 7 kilogram meter per second is equal to mass times VBF. Okay. Divide this down. I'm getting velocity of object B final is it's about this many meters per second. So just read my notes from earlier again, just to save us all a hot minute. Oh, yeah, in fact, it is slower than the original throwing speed, right? Because explosion, one piece goes a little faster, one piece goes a little slower, right? You could have made a bigger explosion and the numbers would change, but momentum would still be conserved. Okay? Let's run a kinetic energy check. Yeah.
How did you get 0.4?
I got it from straight off the paper right here. Told you the two masses. Okay, so it broke not exactly in half. Yeah, right. Okay. So kinetic energy initial. Here, I'll just tell you guys, 1/2 mv squared for the original thing ends up being 112.5 joules. You gotta check my numbers on that for my notes, but okay. Then final, if you do 1/2 mv squared plus 1/2 mv squared, you get 121 joules about. Okay, you guys see an increase in kinetic energy? Hey, that's like Wanda throwing the baseball. There was an increase in kinetic energy. And where the baseball came from her muscles, but from here it comes from a chemical explosion, doesn't it? Right? Or again, if you ran this film in reverse, it would look like a classic collision, in which case the kinetic energy after the collision would go down. Okay? There's one last thing I want to say about this one. Okay, let's take this to the trenches of World War I.
Oh my god.
Right, so here's our trench. Here's like the enemy trench over here. So I'm gonna chuck this grenade. Okay, and I want it to like land in their trench and then blow up and but what if this thing explodes like bam, like exactly where we saw it, like right at the top of the trajectory, right? And then we got different pieces flying all different ways. One piece like flies off, shoot, it overshoots it. One piece, okay, well, it slows down, and so it undershoots. Okay? And if it's an extreme explosion, probably more realistically, what would happen is it would actually go backwards and like land like way back here, right? It's probably what would happen, right? But you know, regardless of what happens, there's a bigger principle that I'm trying to get you guys towards, which is that if you just focus on here, if you look at where the pieces land, there's piece, bing, land there, bing, land there. If you find the center of mass between those two pieces, the center mass lands exactly where the original grenade would have landed if it had not exploded in midair. Okay? In fact, if you only focused on the center mass of all the bits, then you would never even know when the explosion happened, right? Because the center mass would just be never actually changes. Doesn't matter if it's a small explosion or a big explosion or breaks in half or not exactly in half, right? The center mass is just going to follow the actual trajectory. So any little bits, the center mass has to stay where it was. So if you're like hunting around for like, where's the perfect fragments? You can find it that way. All right, so that's a good pause point where we're going to pick up tomorrow with elastic collisions. See you guys then. Have a good afternoon.